Have you ever stopped to think about how a company like Amazon gets millions of packages to the right place at exactly the right time? Or how our power grid doesn't just collapse? Well, the secret isn't magic. It's something called mathematical optimization. It's kind of the hidden engine that finds the best possible answer to mind-blowingly complex problems. And today, we're going to pull back the curtain on how it all works.
See, at its heart, optimization is really just about answering this one single question. Whether you're planning your week, a company is planning its budget, or an AI is figuring out the best delivery route, the goal is always the same: find the absolute best path forward. But what does that actually take?
Okay, so let's dive in. Our journey here begins with a really powerful tool called linear programming. You should think of this as our foundation. It's the blueprint for making a perfect plan, but only in a world where everything is simple, predictable, and, well, follows a straight line.
So what does that actually mean in plain English? Well, let's imagine you're a smart scheduler AI, and your job is to create a work schedule for the lowest possible cost. Linear programming, or LP, is awesome at this, but it comes with a pretty big catch. It has to assume a perfect world. It assumes every hour of work costs the exact same, and it might even tell you to schedule, say, 2.75 people to get the mathematically perfect answer. It's elegant for sure, but it only really works when the rules are simple and never ever change.
Yeah, and as we all know, the real world, it's messy. It almost never fits into those neat, straight lines. Our problems have curves, they have tough choices, and they have a ton of uncertainty. So to solve real problems, we're going to need tools that go way beyond the basics.
All right, let's start by tackling our first real-world complication: the fact that not everything is proportional. Sometimes more of something isn't proportionally better. This is where we need to start seeing the world in curves instead of straight lines.
Let's go back to our smart scheduler. Linear programming assumes that the 8th hour a person works is just as productive as their first. But we know that's not true, right? People get tired. Their efficiency drops off. This is a classic example of diminishing returns. And that's a curve, not a straight line. LP just can't handle that kind of reality.
And that is exactly where nonlinear programming, or NLP, comes into the picture. It's specifically designed to handle these curvy relationships. It lets us build much more realistic models that can factor in things like worker fatigue, the complex physics of an engine, or the wild behaviors of financial markets.
And this is where it gets really interesting. NLP is absolutely crucial in engineering and economics, but it's also right at the heart of so many modern AI systems. For instance, an AI that's managing a power grid, it uses NLP to model the complex, nonlinear way that our energy demand goes up and down, making sure the lights stay on for all of us.
Okay, so we've handled curves, but what about decisions that aren't about how much of something, but are just a simple binary choice, a yes or a no? This calls for a totally different way of looking at the problem.
Our poor smart scheduler has another headache. You see, both linear and nonlinear programming might suggest scheduling 0.7 of a person to get the perfect cost on paper. But you can't do that. A person is either working or they're not. A factory is either open or it's closed. These are all or nothing choices.
And this is the world of mixed integer programming, or MIP. Now, the integer part is just a fancy way of saying we're dealing with whole numbers. This lets us model those yes or no decisions, usually with a 1 for yes and a 0 for no. It's the absolute key to making discrete, real-world choices. And its power is just huge. MIP is used for massive decisions, like where a company should build its next factory or which flight routes an airline should operate. And in the world of data analytics and AI, it's used for something called feature selection, which is basically deciding which pieces of data are important enough to include in a model. That's a critical yes or no decision. So let's just nail this down, because it's a really crucial difference. LP and NLP are great for how much questions, where the answer can be any value on a smooth scale, like 4.5 gallons. MIP, on the other hand, is essential for which one or yes-no questions, where the answers are specific and separate, like 4 workers, not 4.5. Getting this distinction is fundamental.
All right, we've handled curves, we've handled discrete choices, but there's one last giant piece of reality we have to face. The future is unpredictable. To deal with this, we need one final tool, one that sees the world through chances and possibilities.
Okay, let's go back to our smart scheduler one last time. Imagine you've used all these cool tools to create the most perfect, efficient schedule ever made. It's a masterpiece. But then, a snowstorm hits, or 15% of your staff calls in sick.
Your perfect plan, which assumed everything would go exactly as expected, just completely falls apart.
This is where stochastic programming comes to the rescue. Instead of making one optimal plan for one single predicted future, it creates a plan that's robust across many possible futures. It literally bakes uncertainty right into the model. The goal isn't just to be optimal, it's to find the best expected outcome, to minimize risk no matter what the future decides to throw at it.
And you can immediately see how critical this is for any system that needs to be resilient. It's used in finance to protect against market swings, in supply chains to plan for disruptions, and in AI-powered logistics. It helps create delivery routes that can handle unexpected traffic or bad weather, making sure your package still arrives on time.
So how does this all come together? We've looked at nonlinearity, we've looked at discrete choices, we've looked at uncertainty. In the modern world of AI, these tools don't just work in isolation. They're all combined to create truly intelligent systems.
This table is really the perfect summary. We start in that simple, straight-line world of linear programming. Then we just keep adding layers of reality. Nonlinear programming adds the curves. Mixed integer programming adds the yes or no choices. And finally, stochastic programming adds the randomness of the real world. Each one gives us a clearer lens to see our problems.
And this right here, this is the powerful workflow that's driving modern decision-making everywhere. Step 1, data analytics tells us what's going on. Step 2, AI models use that data to predict what might happen. But step 3 is the crucial one, optimization. It takes all those predictions and uses tools like NLP, MIP, and SPAS to figure out the single best thing to do. It's what turns all that insight into intelligent action. So, if you take away one thing from all this, let it be this. These frameworks are so much more than just abstract math concepts. They are the active, logical engines, the brains, really, behind our entire modern data-driven world. And understanding them is a huge step toward understanding how our world actually operates.
And that kind of leaves us with this one big, fascinating question for the future. We started this whole journey looking for the perfect plan. As our data gets better and our AI gets smarter, we're slowly getting better at taming all this complexity, the curves, the choices, even the uncertainty. So you have to wonder, what new, incredibly complex problems will we finally be able to solve? What new, perfect plans are waiting for us just over the horizon?